Good morning once again from Dr. Olson at Daytona State College. This video is the third and final video for Chapter 3 from the Essentials of Meteorology textbook, dealing with air temperature. The first video talked about temperature cycles. The second video talked about factors in daily temperature, and now we're going to talk about applications of temperature as well as measuring temperature. Now, um, when we use temperature for information, it only gives us information if we have some reference point, if we can compare that number with something else. What do we compare it to? We compare it to what is normal. Now, that begs the question, what determines normal? For meteorology, the normal is determined by the average of the previous 30 years of information. Now, this is important for two reasons. First of all, if it's any less time than that, then it's not enough information, and any one anomaly might cause a lot of discrepancy in the data. For instance, if we only did 10 years, so 1990 to 2000, this one very warm year would offset that normal value. So taking more data, 30 years of data, minimizes the effects of any one anomaly. Now, why not take more than 30 years? Well, a couple of reasons. One, quality of data before 1970 was not as good. It was good, but not as good as it is with more modern equipment. Second reason is the Earth is going through certain changes and cycles, very natural and very normal. If we take more than 30 years, we will start to average those trends in as well, which again will bias the data. So we've decided on a nice round number of 30 years to give a good amount of information, sufficient statistically, but not too much information to cause a more drastic difference in the normal from what we are used to. So now let's talk about an important application of temperature data that has to do with heating degree days, cooling degree days, and growing degree days. Now, these three terms are basically just measures of energy needed. Consider this. You have someone at home who needs to raise his house in temperature from, say, 55 degrees Fahrenheit up to 65 degrees Fahrenheit. He's going to need a certain amount of energy to accomplish that task. But then he goes to work and he finds the same need. He needs to increase the temperature from 55 Fahrenheit up to 65 Fahrenheit. But because it's a bigger building and there's more equipment and larger space, he's going to need more energy to heat up his business. So you have differing amounts of energy for the same change in temperature. The idea of the heating degree day and the cooling degree day is to create a base number from which businesses can calculate actual energy needed. So both the home and the business would need to heat their homes by 10 degrees. That's a base number. And then from that, they can calculate how much energy they need to make that change in temperature and do so for the entire year and create an annual budget, including how much money they need to set aside for heating and cooling their building. So let's start off with heating degree day. How does a heating degree day work? Well, simply, how many degrees do I need to warm up my house to reach some certain temperature? Most often we use the temperature of 65 degrees Fahrenheit. So how do I do this? Well, let's take a simple day where the high temperature is 40 degrees and the low temperature is 30 degrees. Rather chilly day. So easiest way to do this is take the average temperature. So if your high is 40 and your low is 30, take the average, the number right in the middle, 35 degrees. Now, I need to increase my temperature from 35 to 65. That is a difference of 30 degrees. So I have to increase my temperature by 30 degrees. Therefore, it is a 30 heating degree day. So how would we do this budget-wise for a company? Let's say that today is a 30 heating degree day and you have an entire month where on average your daily temperature is average 35 degrees Fahrenheit. That means 30 days at 30 heating degree days each day, you have a total of 900 heating degree days for the whole month, 30 times 30. What if you do that for a whole year? On average, you are at 30 heating degree days for an entire year. Well, 30 times 365 comes out to roughly 5,000 heating degree days. And then using that number, a business can calculate how much energy they really do need to spend to heat their business. Now here's a cool map showing the nation and describing how many heating degree days they normally have every year. You can see in the northern states, they're upwards of 8,000 to 10,000 heating degree days for an entire year. Fair amount of energy needed for heating, and that makes sense since it's colder up there. Now look down in Florida, here at Daytona Beach, we are pretty much right on that 1,000 heating degree day line. It's pretty much where we are. So not as much information, not as much energy needed for heating here in Florida. Makes sense because in the summers it's hot. You don't need to heat buildings in the summer. So pretty much that 1,000 heating degree days is for the months of January and February. Cooling degree days work the exact same way, just opposite. How many degrees do I need to cool down my house to reach 65 degrees Fahrenheit? So again, take a simple example, high of 90, low of 70, that means the average temperature is 80. So if I go from 80 down to 65, that means I drop the temperature by 15 degrees. It is a 15 cooling degree day. Oh. I had a figure, and there is a figure in your book that shows the average cooling degree days for the nation on an annual basis. And obviously that number is higher for Florida, and it would be lower for states in the north. Okay, so what is a growing degree day? A growing degree day is very similar to the heating degree day and cooling degree day. But the heating and cooling degree days are meant for heating and cooling businesses and homes, where the growing degree day, the energy is applied to growing plants. So the way we calculate it is the exact same way as we do with the cooling degree days. But the base temperature now is going to change depending on what plant we use. Here's a table from your textbook that does talk about different plants and their base temperature. So for example, let's say corn. Corn has a base temperature of 50 degrees Fahrenheit. Take the same example we just did, high of 90 and a low of 70, which means the average temperature is 80. That means I am 30 degrees over my base temperature. That's basically a surplus of 30 growing degree days. That's how much energy the plant is going to absorb for the day. But plants need more than that to mature. So corn, for example, will need a total of 2,200 to 2,800 growing degree days to mature. So in order to reach that 2,200 growing degree days, I will need at least 75 similar 30 growing degree days for the corn to reach maturity. And that number right there, the 75 days, and the number, the base temperature, all of that information helps to determine when is the best time to plant crops. Very, very, very useful information for agricultural reasons. Now, if you want to know any of these values for Daytona Beach, heating, cooling, or growing degree days, I have that information for you. If you go onto Falcon Online, go onto the content page, under weather files and links, there's a sheet called Daytona Beach Climatology. That information, along with average temperatures, average precipitation, so on, those normal values are available for you on Falcon Online. Let's finish up the video talking about how we measure temperature. Well, temperature, let's talk about perception of temperature first. Temperature can feel very, very different depending on the weather around you. For instance, you've all probably noticed a temperature of 60 degrees Fahrenheit in March will feel rather warm after winter. Whereas a similar day in November, where the temperature drops to 60 degrees Fahrenheit after summer, is quite cold. It's the same temperature, but it feels different. Why? The reason is what we call the metabolism. In winter months, your body or your metabolism is used to colder temperatures, so a temperature of 60 feels warm. Whereas in November, your body is used to summer months being warmer, so your metabolism is used to that. So 60 is a drop in that temperature. It feels colder, even though it's the same temperature. Here's another effect on metabolism. It's called the wind chill. Now, basically what happens is when you are standing out in wind, the wind passes over your body, causes evaporative cooling. The wind passes by and it induces evaporation much quicker, and the evaporation will then cool your skin a little bit more, thus cooling, the body will perceive temperature to be a little bit cooler than it really is. Simple example, let's take 40 degrees Fahrenheit. That would be here at the top left of your figure. If you increase the wind speed to 5 miles an hour, the body will perceive the temperature to drop by 4 degrees down to 36 degrees Fahrenheit. But if it's minus 40 degrees Fahrenheit and you have a 5 mile an hour wind, you see that the temperature now drops by 17 degrees. So you have a perceived temperature, or a wind chill temperature, of minus 57 degrees. So the effect is much stronger at colder temperatures and slower wind speeds. You can see that at larger wind speeds, you don't have as big of a drop in temperature. It is quite dropped from the actual temperature, but from 50 to 55 miles an hour, it's not a big drop. So bottom line, wind chill causes a drop in temperature, and that drop is most affected, or most apparent, excuse me, in colder temperatures. Now, that leads to a huge health problem called hypothermia, because even though the temperatures could be warm, bringing in the wind will cause the body to cool much quicker than it should, and could induce the body into hypothermia, which is where the body temperature is now dangerously lower than average. All right, we're actually out of time for this video, and I'm going to need a little more than a couple of minutes to complete the last section, so I will come back in one 5-minute video to finish talking about the different ways that we measure temperature.